Welcome to the course on data structures and algorithms. Today we'll look at the problems based upon binary search tree. Before starting with its problems, we will start with what is a binary search tree. Binary search tree is a binary tree with following properties. So the first property is all the atoms in the left part of the tree are less than the root, and all the atoms in the right part of the subtree, they are greater than equal to the root. As in the first case, all the elements in the left are less than the root. Here all the elements in the right subtree are less than equal to the root. Basically, a provision of less than equal is to add the duplicate elements, or is to think of duplicate elements into the right part of the tree. In this binary search tree, as earlier mentioned, right or left subtree contains keys or the elements, they are less than the root, and right subtree contains the keys, they are greater than equal to the root. Schematically, this is represented in this figure. K is the root. Basically, in the left part, all elements are less than k, and in the right part, all elements greater than equal to k. Now, there are few examples or valid examples of a binary tree, of a binary search tree. Let's say there is only one node with a value 17. It's binary search tree. Now 17, 6 and 4. This is also a binary search tree. 17, 6, 19, 5 is also binary search tree. Means all these trees, they are valid binary search trees. Now with this little introduction of binary search tree, we'll start with different operations to be carried out on a binary search tree. Basically, there are few important operations one can carry out on a binary search tree. The first operation is traversing a binary search tree. Basically, traversing of a binary search tree is having a unique significance with a traversal. So what's that? We will see later on. Now think of this traversal operation. Now, whatever operation we carry out in a binary search tree, every operation starts with a root node. Now, to have a traversal operation in a binary search tree, let us draw some outline, which will act as a path to visit the different nodes present in a binary search tree. On this line, I have marked 1, 2 and 3. Means I have marked that one line, 2 lines or 3 lines. Basically, 1 means things to be recorded in the first digit. 2 lines means things to be recorded in the second digit, and 3 lines means things to be recorded in a third digit. Now let's think of this binary search tree, which is rooted at 23, left subtree which is rooted at 18, and right subtree which is rooted at 44. And left subtree is having 2 child, 12 and 20, and right subtree which is having again 2 children, 35 and 52. Now let us try to record the things in the first visit, second visit and third visit. Whatever things we are recording the first visit, they are only first visit we are talking about. 23, 18, 12, 20, 44, 35, 54, 52. Basically, this is called as pre-order traversal of a tree. Now same tree will be traversing and we are recording the things in a second visit to the individual node. So in order to record the second visit, we got, or in order to get things to be recorded in the second visit, we got a 12, 18, 20, 23, 35, 44 and 52. If you look at this carefully, it is observed that whatever things we got in the second visit, generally this second visit recording is called as in-order traversal. And if you look carefully at this, we identifies this is a ascending order. This is a sorted list. Means in-order traversal of a binary search tree, it leads to a sorted sequence. Now we'll go to the next stage where we'll be recording a nodes in a third visit. If you try to record the nodes in third visit, we got 12, 20, 18, 35, 52, 44 and 23. Basically, this third visit recording is called as post-order traversal. Now pre-order traversal and post-order traversal of these kind of the trees, it doesn't signifies much, but if you record it's a second visit that leads to the sorted sequence. This is the importance of binary search tree. Now second operation to be performed on a binary search tree is a search operation. Basically, that searching operation might be for getting a smallest element, getting a largest element, or finding some requested element. Now, to get a smallest element, what we do? As earlier I told, in case of binary search tree, we'll be organizing the nodes in such a way that whatever elements in the left subtree, they are less than the root, and elements in the right subtree, they are greater than equal to root. If you take this thing in mind, if you keep this thing in mind and think further, one can understand, one can say, to get a smallest element from a binary search tree, traverse the tree in leftmost portion till we get left and right both null. So that is our smallest element. Now in this tree, which is rooted at 23, it is clear that 12 is the smallest element, and basically 12 is the leftmost element of that particular tree. Now, based upon this, we'll make the conclusion that smallest element of a binary search tree is located in the leftmost branch of the tree, and definitely a largest element of a binary search tree is located in the rightmost part of a tree. That is quite clear. Now let me see an algorithm which is going to find out a smallest element. To find out the smallest element, we'll start with the algorithm, and that algorithm name is find a smallest from a binary search tree. As I told that smallest element of a binary tree binary search tree is located into the leftmost portion, so that we are passing root to the binary search tree or to the binary search tree algorithm. And first of all, we'll check that if root left is null, means nothing is there in the right part, then directly return that root which is the smallest element. If it is not, means root left is not null, then root is equal to root left, means we move down to the leftmost portion, means we changed our root to the root of left subtree, and that is passed recursively to the algorithm, that is a find smallest BST algorithm. So it will again go off, then it will check that root left is null. If it is null, then it is going to return root. Otherwise, it will do root is equal to root left and again pass that new root to the algorithm. Basically, this is a good example of an recursive representation of an algorithm for finding a smallest element in a binary search tree. Now, if you look at it's a timing analysis. Basically, job of every engineer is not only to write the algorithms, but to analyze them in order to find out which is the solution of optimability. Now, to do the timing analysis of this binary search tree, let's think of this binary tree is a balanced and its height is h. Then timing analysis is, or it takes time to get an element, smallest element, which is equal to height. Now, based upon this, the complexity of searching operation, searching of a smallest element in a complete or balanced binary search tree is equal to big O of h. But height of binary search tree is based upon a factor n, and n is number of elements we supplied, so that the complexity is going to become big O of log n. If the binary search tree is not a balanced, then in worst case the height is equal to the number of nodes present in a tree. Then the complexity is going to become directly big O of n. If the binary search tree is a left skewed or right skewed, then we'll get a thing like a linear representation. And so because of that, the complexity of an algorithm gets equal to big O of n. Similarly, there is another algorithm that is to find a largest element from a binary search tree. As earlier I told, to get a largest element from a binary search tree, one need to traverse to the rightmost part of the binary search tree. And to understand this, let's think of an algorithm of finding a largest element from a BST. We are passing a root, and first thing is we'll be checking root right is null. If root right is null, then directly we are returning a root. If it is not, then we'll be changing our root to the right. So root is equal to root right, and then passing that new root to the find largest BST. And this algorithm is a recursive algorithm. So this algorithm will return a largest element in the tree traversal, and that too recursive. Then the timing requirement of this operation depends upon the following. The first thing is, if a tree is a complete binary search tree, then the complexity, then the time requirement is equal to the height of the tree, and generally height of the tree is log n. Here n is number of elements. Means all other timing analysis is as equivalent as to the finding a smallest element. Now, the next point is to search any particular element. Not a smaller, not a larger, but some another element. Now to get into this, we'll have some algorithm. And that algorithm accepts two things. One is a root of tree, and second one is a key to be searched. Basically, key to be searched means a key we want to search either, or we want to locate either in the left subtree or in the right subtree. To proceed, first of all we'll check if the root is null. If it is null, directly we'll print the message that the tree is empty. If it is not, then we'll check that whether that key is less than root data. If that key is less than root data, then directly we'll go to the left part. Otherwise, we'll go to the right part of the tree. And this process is continued till we get the desired element. Basically, our search will terminate positively or negatively. If our search terminates positively, means we are getting a key, and our search is going to terminate negatively, means we are not getting a key. We traverse a tree till all the leaf nodes and we are not getting it. Basically, these are the three searching operations we have seen today. The first searching operation is searching a smallest, searching a largest, and searching a given element. Okay. Today we'll stop at this point and we'll come to the next in the next session.